All right, guys, let's get started. Today is Monday, October 26th. It's an A-Day. We had a warm-up, so make sure that you guys completed the warm-up. Hope you guys had a great weekend. I know I did. We went camping and did some fishing. My daughter caught her first fish, so that was great. We went to Tyler and stayed in my father-in-law's trailer, which is like a RV essentially that you haul or you tow. So that was fun. It was a good weekend. Nice weather. So we're going to talk about kinetics. I'm going to review a little bit since it's been a little bit, and then we're going to push kind of through the whole chapter, hitting a little bit of stuff, and then I'm going to kind of decide what we need to revisit, and we'll revisit stuff on Wednesday, hit some free response. And then we'll be planning for a test. I haven't decided when that's going to be, but we're looking at a test either Friday or Monday next week. And I'm going to post the test. I think I'm going to give you guys a class period, and we'll do both parts of the test during the class period. So we'll schedule that and just make sure that you get that in your calendar and you're ready to complete the test during class. We're not going to do it as a take-home test because we got a lot of other stuff going on, but we're going to do a test during class, okay? So we can practice the timing skills. You'll be able to make up the test, you'll be able to do corrections and stuff, but I do want to practice the time constraints, okay? So before we get into the content, let's have a look at Canvas, and let me show you a couple things that I did last week when I was working on stuff. So go to AP Chem. I made our calendar for the next week. I assigned homework. I assigned the Chapter 6 problem set. So I'll have that. And then if you guys want me to make an answer key for Chapter 3 through 4 problem set, we did that one a while back on stoichiometry and solutions. If you guys want that, please just let me know, and then I will make it. But I don't want to make them if you guys aren't going to use them, because that's going to take a good 2 hours to go through that problem set. That's a long video. So if you want that, I will be happy to do that. But I think it's probably more efficient if you guys want to come into tutoring and one-on-one work certain problems, right? And that would save a lot of time. Same thing with Chapter 6. If you guys want me to go through the whole thing, I'll be happy to make a video and send it out to everybody after they're all turned in. But you guys need to let me know that you need that, because that's a lot of extra time for me to do that if we're not going to use it. So if we're going to use it, I'll be happy to do it, but I just need to know ahead of time. So today we're going to be hitting review, collision theory, and half-life. We're going to talk a little bit about integrated rate laws. We're going to talk a little bit about mechanisms. There are no new assignments due today. The Chapter 6 homework is due Wednesday, so I'm trying to give you enough time on this. So Chapter 6 homework is due Wednesday, and that is, let's see, that's going to be a test grade. So instead of giving you a test over Chapter 6, I want to give you a homework to practice, kind of master those skills, and that way we can kind of go ahead and move on. And I don't want to just do a test on Chapter 6. So I'm going to just make that homework a test grade. Okay, and then the lab, precipitates lab that I gave you guys is due Friday. Some of you guys have already turned in both of these, so you're doing great. I'm also going to go ahead and sign the Chapter 1 through 3 AP test, multiple choice section, just the multiple choice section. So this is going to be a review of Chapters 1 through 3. It's going to be 25 multiple choice questions. I'm assigning it today. I will get it out to you guys during third period, and then it will be due next Monday. Okay, so you will have a whole week. You'll have 1, 2, 3, 4, 5, 6, 7, 8 days. Okay, so I have 8 days to complete that. And then I also already have the Chapter 12 problem set completed. Notice that it's a link and you can click on it. And so you can click on it, click here to access the homework, submit it through Canvas, please. So this is due Monday, November the 2nd, which is next Monday. And it's kind of short, it's not too bad. It is those questions there. Okay, practicing calculating the rate law, determining the rate constant, and hopefully this shouldn't be too bad. It should be pretty quick. That should be good. And I'll be getting another Chapter 12 problem set out to you guys kind of as we get through it, probably next week, although next week we'll be wrapping up kinetics. Should be getting into our next chapter. What is our next chapter? I want to say it's supposed to be equilibrium. I think so. Okay. But there are some labs I kind of want to do, but we'll see what we can do. We'll have to just kind of play it by ear. So that's the homework. What else did I put in here? On Wednesday, we will continue talking about kinetics. Chapter 6 homework, what we do. On Friday, we'll finish kinetics and the precipitants lab, what we do. Maybe we'll do a lab on Friday, the heat warmer lab or something. I'd like to do that one. Let's see. It's only so much time in the day, so I can only plan so much. Doing our notes and our assignments and all that takes so much time. It's difficult for me to get a lab together each week, but I'd like to, so that we're doing something kind of interactive. Okay. Let's go back there. My Blue Angels. Okay, that's the NIMSY notes there. Here's our PowerPoints. Okay. So what are the factors that affect the rate of reactions? First thing is concentration. The initial concentration of the reactants will influence the rate. The higher the concentration of those reactants, the higher the rate. The higher the temperature. More temperature, faster rate. Heat them up, speed them up. Okay, if you have a catalyst, the presence of a catalyst will speed up the rate of the reaction. And maybe at the end of this video, I'll show you guys some catalysts. I need to do that. Or maybe during class, because I got to find the videos. All right, and then the catalyst acts by lowering the activation energy. It's not consumed like a reactant. It's present at the beginning of the reaction. It enters the reaction and interacts with the reactants to change their pathway for the reaction, and it speeds up the rate. So it changes how they're going to react and what path they're going to take. And then the catalyst is actually available at each step, and so it's produced at the beginning, or it's introduced at the beginning, but then it's kind of present each step. It doesn't disappear like an intermediate. Intermediates will disappear and cancel out. Catalysts are present for every step, so it can be used again and again to speed up the reaction. So here's our activation energy right here. Here's our activation energy here, and so it's going to lower that activation energy. It's going to speed up the rate. 1 second. Let's turn that off. Noisy. Another word for a catalyst that's used in biology is an enzyme. An enzyme is a biological catalyst used in the body to speed up processes. The rate will increase if the surface area is increased. Think about dissolving sugar. If you take a large sugar cube and put it in coffee, it's going to take a little bit to dissolve it because it can't get to the middle. It can only act on the outside. But if you take a sugar cube and grind it into a powder, well, then all that surface area is increased exponentially, and you put it in the coffee, and then the coffee can attack each of those cubes. So that's a lot more surface area, and it's going to dissolve a lot faster. And that's why we use powdered sugar. That's why when we go to the store and buy sugar, it's powdered or small crystals so that it'll dissolve. What else? Mixing. If you mix and stir something, the rate of the reaction will increase. Okay, the rate of a reaction is expressed in molarity per second, so moles per liter per second. Let's write that out so that we all know what that means. Moles per liter per second. That is the unit for rate, and it is the change in the molarity. Change in the molarity for the substance, let's call it X, divided by the change in time. So how does that concentration change over time? And it turns out as a reaction happens, the rate is not constant. And you guys got to understand that. The rate is not constant. We can calculate the initial rate of the reaction given the initial concentration of the reactants. But as the reaction proceeds, the reaction is not constant. So it'll increase in speed. And that's why if you look at the graphs, that's why they're curved. They're not a linear relationship. This is a curved graph, exponential. All right, and so as the reaction goes on, as you guys can see here, the concentration is going to exponentially decrease. Right, and so that's because the reaction is speeding up, consuming more and more reactant over time. This is time. This is the change in the concentration, right? Brackets, maybe moles per liter. Okay, now how can we find an instantaneous rate? We can put a tangent line on here, which is a line that only touches that point. So if I wanted to know the concentration of a reactant at this time t, whatever it is, I could put a point there. I could make a line at that point to where it touches the graph only at that point, and then I can get the slope of that line. Slope equals rate. It's very important to understand. The slope will equal the change in the concentration over the change in time. We could put x in there if we wanted to. Okay. Okay, now if it's like this, then this is a product. You have very little product at the beginning. Reaction will start producing products, and as more and more products are produced, the reaction actually speeds up. Okay. Okay, so positive and negative. Reactants are negative, products are positive. Instantaneous rate is the reaction rate at any given time. It's equal to the slope of the concentration at any point. So I can plot a point, get a tangent line. I can pick 2 points along that line, find their coordinates, and find the slope. Rise over run. Slope equals rate, and that is equal to the rise over the run. What does that mean? The second y value minus the first y value divided by the second x value minus the first. y2 minus y1 over x2 minus x1. So I'm going to take my first y value. This one has the higher concentration, right? This one's further up the graph on this y-axis. So I'm going to say that this is my first y value. This is my second y value. So I'm going to do x1 minus x2. That's my rise divided by, right, because that's the difference in this right here. It's the difference between those 2 points in terms of the y-axis, divided by my run. My run will be T1 minus T2. And that'll be the difference between here and here. Okay. Coefficients in the balance equation are used when comparing rates for substances in a reaction. So I covered this, but I think I did a poor job. I'm not happy with the job that I did, so I want to hit this again, and I want to be a little bit more clear on this. So let's say in an example, at a given time, the instantaneous rate of appearance of nitrogen dioxide, which is NO2, if the rate of appearance is 3.2 times 10 to the minus 6 molarity per second, find the instantaneous rate of disappearance of nitrogen monoxide and oxygen at that time. All right, so here we go. We got this, this, and this. 2 moles of nitrogen monoxide are going to react with 1 mole of oxygen to form 2 moles of nitrogen dioxide. Okay, so we know the rate of appearance of this substance. Okay, and so we kind of said, okay, if it's 2 to 2, then that's a 1-to-1 ratio between the coefficients in these two substances in the balance equation. And so the rate will be a 1-to-1 ratio. The rate will be the same. Okay, and then oxygen will be half of that because it's like this. It only has a 1 there. So let's write this another way. And the trick that I saw in the NIMSY notes, I watched the NIMSY notes today, took forever, but I learned a lot, and I was able to, kind of review. And so what we can do here is take the coefficients and make them the denominators. Okay, so if I want to know the rate of NO, this guy, if I want to know the rate of that guy, I'm going to make this a denominator. I'm going to write 1/2 times the change in the concentration of NO. So that's my rate of NO. And it's going to be minus because it is a reactant. So that's my rate of that guy. And then I can say, okay, the rate of that will also be equal. So the overall rate of the reaction will be minus 1/2 the change in the concentration of NO. The rate of the reaction, not just with respect to NO, but the overall rate of the reaction will also be equal to 1/1. So we take this coefficient 1 right here, put it as a denominator, so that 1 is on the bottom. So it doesn't matter because 1/1 is 1 anyway, but it's going to be times the change in the O2 concentration. Okay, so notice that the concentration of NO, the rate of that will be 1/2 of O2. And then we can write it for a product. We can say it's going to be positive. Now this one's positive. Wait, this one's a reactant, so it's going to be negative. So this is going to be negative. Okay, so this is going to be the expression for the relative rate of nitrogen monoxide disappearing. Okay, the coefficient will turn into a denominator. Coefficient, denominator. And then same thing here. This is a reactant. It's going to be minus. This will be the expression for the relative rate of oxygen disappearing. It'll be twice the rate of nitrogen monoxide. And then what is the rate of NO2 production? Nitrogen dioxide. It's going to be plus 1/2 change in NO2 concentration. Okay, so that's our 3 relative rates for this reaction. And you can see that the rate of this guy, this is a minus exponent, so a larger value means a smaller number. Okay, so this is actually 1/2 of this. Let me try that in the calculator just to make sure. But if I do, and I think the way that I explained it last time, I think I said the opposite. So this is minus 1.6 e to the minus 6. If I divide that value by 2, no, that doesn't work. This times 2. If I take this guy and divide it by 2, then I get that guy. So yeah, that is right. Okay. I'm just confusing myself, I guess. So since the O2 only has a 1 on its coefficient, this guy will be twice this guy. Okay. All right, the reaction rate is proportional to the concentration of the reactants. So we can write a rate law or a rate expression. We can call it rate law. We can call it a rate expression that shows how the rate depends on the concentration of the reactants. It has a rate constant K. This is a value that depends on temperature. The higher the temperature, the higher the rate constant. All right, this is the form. Rate equals K. That's baby K, lowercase k. Make sure that when you write it on the AP exam that it looks like a lowercase k. All right. And then it's going to be multiplied by the first reactant raised to some power, the order for that reactant, times R2, concentration of R2, raised to some order for that reactant. M and N are called reaction orders. Their sum is called the overall reaction order. And these reaction orders are determined experimentally. We have to measure the rates of the reaction under different circumstances and then determine what those orders are. All right, usually we have 0 order reaction, first order reaction, or second order reaction. Sometimes they can be fractions, so don't flip out if you see one as a fraction. And that just means that the order is a fraction, which means like if it was 1/2, if the order was 1/2, that means that it's raised to the power of 1/2, which would be the square root. So it'd be the square root of the concentration. Okay. All right, if a reaction is 0 order in a particular reactant, changing the concentration will not affect the rate as long as there's some of the reactant present. So as long as you have some of the reactant present, if you double the concentration, you get no change in the rate. First order is a direct relationship. It's linear. That means if you double the concentration, you double the rate. If I change the concentration from 1 to 2 times, the rate will change from 1 to 2 times. If I half the concentration, then I half the rate. Now, second order is an exponential or a squared change. That means if I triple the concentration, I take the 3 and I raise it to the 2 power. I square it, so it's a squared change. So if I triple the concentration, I get 9 times the rate. Or if I do 3 squared, we get 9. What if I doubled the rate? I'd get 4. I'd get quadruple. Okay, by just that one reactant. The other concentrations of the other reactants are going to be held constant. You can only change one at a time. Now, if I half the concentration, then I get 1/4 the rate. So how do we do that? How do we go from 1/2 a concentration? If I have to take 1/2, raise that to the squared, I get 1/4. Okay. All right, and then this is what third order would be cube changes, and we won't see third order. The rate constant is not affected by the concentration of the reactants, but it is affected by the temperature and the presence of a catalyst. All right, so here's an example. H2 plus Cl2 makes 2Cl. So let's find the overall order of the reaction. So if we take the first, let's look at chlorine. So here, chlorine, we're going to compare A and C. All right. So let's compare A and C in the table. So if I double chlorine, keep this constant, no change, what happens here? It multiplies by 2. So what I can do is I take the change in the concentration raised to some power, and I say that's going to be equal to the change in the rate squared. Okay, and so what goes in here? The change in the concentration is 2. So 2 to the x is equal to 2 raised to the 2. Okay, and so that's 4. 2 raised to the x is equal to 4. So x must be, wait, this is right to the 1. Let's see. If I change the rate to power and set it equal to the change in the rate, let's just change that to 2. There we go. Change that to 2. There we go. Okay. So 2 raised to some power is equal to 2. So x must be equal to 1. And that means that it is first order with respect to chlorine. Okay. Now let's clear it and do the same thing with hydrogen. Hydrogen, we double it there, but we want the other one constant. So I think we need these two. Yes, we want these two. So let's look at the change in concentration of H2. It's going to double. This is constant. We've got to check that it's constant. And then this is a times 4. So we set the change in the concentration raised to some power. We set that equal to the change in the rate. So this is the formula. I keep trying to get this formula. I keep screwing it up. But the change in the concentration raised to the power of x is equal to the change in the rate. So the change in the concentration was a doubling. So 2 raised to the power of x is equal to 4. So what is x? X must be 2. Okay? And so the rate order for hydrogen is 2. What's the overall order of the reaction? It's equal to the 2 plus the 1. That's a 3. So the overall order of the reaction is 3. Okay? And so if we write our rate law, this is what our rate law is going to be. Since the order of H2 is 2, it will be squared in the rate law. We would have to square that concentration in the rate law because it affects the rate squared, right? It affects it exponentially. When I double the concentration of H2, it quadruples the rate. So I must put a square there to account for that. And then chlorine was first order, And so it's just chlorine with brackets around it. And if you want, when you write it, and I actually do this, I will put a 1 up there, but you don't have to. You could just write, so let me write it. Rate equals K, and maybe you can make this look like cursive, like a little K. Or you can write it like this. Just make sure that you don't write the same little k as a big K when we do equilibrium, because we'll have a big K. So H2 squared times chlorine. So you can write it like that. That's fine. Or if you want, you can put the 1 there. Okay. Now, before we do the units for the rate constant and calculate the rate constant and all that, I want to explain how we would answer a question here. So the question is, what is the rate law? And justify your answer. Okay, so let me talk through this. And I almost want you guys to take notes on this, because if you could get the wording of this just right, excuse me, you can get all the points. If you don't get the wording just right, then, or if you shorten this, then you may not get any points at all for the justification. Okay, so how do we justify our answer here? How did we get this? All right, first let's look at chlorine. All right, so how would I say this? When the concentration of chlorine is doubled by comparing experiment A and experiment B. Okay, so when I compare the concentration of A to B for chlorine, it doubles. So when the concentration is doubled from experiment 1 or experiment A to experiment B, while the concentration of H2 is held constant between experiments A and B, the rate between A and B doubles. The rate goes from this number to this number. And so we see that the rate doubles, the concentration doubled, and so that is a first order with respect to chlorine. Now for the hydrogen, we have to compare experiment B to C. We see that the concentration is doubled while the concentration of chlorine is held constant, and we see that the rate from experiment C is 4 times the rate from experiment B, which is a second order with respect to hydrogen. And then I got my overall order of my reaction, and I got my rate law. All right, so just practice justifying that. We'll do some of that as well. Okay, here are our units for the K. So we did this algebraically, but I also showed you guys a trick. And the trick is the concentration is 1 over m to the x times a second. And x, the exponent on the m, this one's a 2, right? Whatever that value is for x, it will be 1 less than the overall order of reaction. Notice in this reaction we had an overall order of 3. Notice that that is squared. It is 1 less than the overall order. And that is just so that it cancels. Because we've got molar here in the rate, and it needs to cancel with one of them. Okay, because this is m to the third. This is m by itself. And so if we have m to the third, one of them will cancel, and we get m to the 2. And I think one of you guys was asking why, and that's why. It's because that's the way for it to cancel. All right, so we can write that as our units for this rate constant. 1 over m raised to the power of x, where x is 1 less than the overall order of the reaction. Not the order of each reactant, but the overall order of the reaction, times the time. Notice that in this table, we use seconds. So you got to look at the table and see whether you're using seconds or minutes. Sometimes it'll be seconds, sometimes it'll be minutes. It depends on what's more convenient. And so if this were minutes here, we would write minutes instead of seconds there, okay? Now another thing we can do is we can write L to the x over moles to the x times the time, where again, x is 1 less than the overall order of the reaction. So if we were to write our units here for this K that we're calculating in this example, it would be liters squared divided by moles squared times second. It's 2 because that's 1 less than the overall order of the reaction. That's exactly what we need K to be to cancel with the units in this rate law. And it's seconds because we are using seconds right there. It's molarity per second. All right. Rate laws can be converted into equations that give the concentrations of substances at any time during the course of a reaction. First order reactions will have this form. The rate is equal to K times the concentration of A. There is no exponent. It's a 1. That means that the concentration of A will not change the rate. What changes the rate? The rate constant, K, which depends on temperature. So that means the only way to speed this up is to increase the temperature, which will increase K. The concentration of A will not change it. Okay? How do you find the reaction concentration over time? All right, so this will give us the rate. This is an average rate. So all the stuff we've talked about so far with this table and all this stuff we've been talking about, all this stuff here, this is the average rate of the reaction. And this will give us the average rate of the reaction overall. So from the beginning to the end, what is the overall rate? Okay, it doesn't tell us what the rate will be at any given time. So in order to do that, we have to do something called an integrated rate law, which is what this is, integrated rate law. And essentially, and I hope I don't confuse you guys here, essentially what we're going to do is we're going to take a graph, we're going to take a curve. When you do an integrated rate law, essentially what we are doing is we are integrating, which is I know is a calculus term, but we are taking the area underneath this curve. We're taking this area, and then we're going to divide it up, and we're going to take the area of each segment under the curve, take the area under the curve all the way, and then we add all of that up. Each piece. What's the area here? 1 plus 2 plus 3, and you add it all up. And that's what integration is in calculus. You're taking the area underneath the curve, and then you're adding it all up. And that's how you get the area under the curve. That's how you get the rate, okay, at any given time. Okay, so the rate law for the first order, which remember a first order reaction, first order, sorry guys, I was messing up. First order is where the concentration will affect it, but it's direct. That means if this doubles, this doubles. I think a minute ago I had said that it doesn't affect it. This is a first order. It's the zero order that doesn't affect it. So zero order, let me look at my notes. Zero order reactions will have the form, so zero order rate will be equal to K. Sorry about that, guys. So zero order rate is equal to K only. There is no concentration of the reactants in there. The reactants have to be present for the reaction to happen, but the concentration of those reactants does not influence the rate. Now, first order reactions depend on the concentration, and it's linear. Linear. So if you double the concentration of the reactant, you double the rate. All right. Now, if you're going to find the reaction concentration over time, you have to use the integrated rate law, which looks like this. What does this say? There's two forms of it. This says that the natural log, ln, which is a keyboard on your calculator, natural log, which is log base e is what that actually is. Natural log ln on your calculator, okay? Natural log of the concentration at time t will be equal to the natural log of the initial concentration of your reactant. So that means initial. The little O there, initial. So that's the initial concentration when you started the reaction, minus the rate constant times the time. How much time has elapsed? So you plug in the time here, usually seconds. You plug in the rate constant there. You plug in the initial concentration there, and this will equal the natural log of the concentration at that time. And how do you get the concentration of AT? That will be equal to this is the natural log. So you need to take the inverse of the natural log to get this by itself. So that'll be e raised to the natural log of this. E raised to the power of what? 1 second. Natural log. Let's just, so the natural log of this. So I think you just take the natural log of this guy. Now, how do you get rid of a natural log? I think you do the inverse of a natural log. So you're going to do ln minus 1 of all that, ln of the concentration of AT, and then that will cancel with that. So I think, or no, it's just the natural log of that. So you just type it in the calculator, natural log of that concentration, hit equals, and you get the number. I'm overthinking this. So you're just going to type in the calculator ln of the concentration. So if my concentration was 2, I'd write ln parentheses 2, and that'll give me a number. Okay, and actually this is 0.693. So if my concentration was 2 molar, my this would be my concentration here, 0.693. Okay, and this is another form of it. KT, the rate of the reaction, or the rate constant, times the time that we're looking at, is equal to the natural log of the initial concentration divided by the concentration that we're solving for. So this is going to be the concentration at time t. Whatever that time that we say we wanted to look at the concentration at 5 minutes, then this would be the concentration at 5 minutes. So this would be the final concentration, or the time, or concentration at time t, whatever that time may be. So if we plot the graph for this, if we plot a graph, and here for this part of the notes, integrated rate law, the graphs are pretty much it, and using these equations. So we'll have some practice using these equations. If we plot a graph of the concentration of AT, the concentration of our reactant over time, and we get T, we will get a negatively sloped line, but it'll be linear. And we can find the slope of that line by doing rise over run, right? Change in the concentration of AT over the change in time, right? Y2 minus Y1 over X2 minus X1. So we can find our slope, and that will be our rate, and it'll be a straight line. It will have a negative slope because we're looking at a reactant. This is for a first order reaction. So first order reaction will have a linear negative slope line. So it'll be a straight line. It'll have a negative slope. And the slope of that will give us K. The slope will be equal to K, the rate constant. The slope will be minus K because it's going to be a, because K can't be negative, and so we have to flip the sign. So since this slope is negative, right? So you're going to go back, previous. Yeah, here's my graph. So it's negative slope, but K can't be negative, so we got to flip the sign of K to make it positive. Okay. All right, here's our reaction. CH320. Trying to think what that is. Will decompose to make methane, CH4 plus H2 plus Cl. This is a first order process with K equals to this, and with the initial pressure of 256 torr. That's the unit of, that's one of the units of pressure. We can do this equation. We can do this problem just like we would do it in concentration. Although I almost never see it with pressure. So this is a rare example where we're seeing it with pressure. And then we want to find the partial pressure of this substance after 36.5 minutes. So a parallel for this example that's familiar to you guys would be, here's our reaction. We're given the balanced reaction. We're given the rate constant. We've got it. And then we're given the initial concentration of this reactant. And then we want to find the concentration of our reactant after 36.5 minutes. It's just that in this example, we're doing pressure. So how would we do this? All right, so for gases, the pressure will be kind of similar to moles, and so we're going to use concentration. All right. Actually, we're just going to use concentration because the pressure on a gas is directly related to its moles. I'm trying to think who said this. Probably Avogadro. I think this is Avogadro's law, saying that the pressure on a gas is equal to the number of moles that the gas has in the container. So this is our first integrated rate law for our first order reaction. ln of the concentration, initial concentration, divided by the concentration at time t. So this is our, do we have initial? Yeah, here's our initial pressure. This is our initial pressure. And then this is our final pressure, PT. And I keep saying final, but I mean pressure at time t. Not necessarily at the end of the reaction, but at a certain time. Okay, so here, this is KT. I'm going to annotate this a little bit. Okay, so what did we do here? We have our reaction. K is right here. There's K. Let's put brackets around it, make it a little nicer. Here's T, 2190 seconds. Where did we get that? 36.5 minutes. 36.5 times 60. We get 2190. So I had to convert it to seconds because the value of K is per second. And so we got to convert this to seconds. That's 2190 seconds. We did 60 times 36.5, and we get that. Right, 60 seconds in a minute. All right, so that's KT. We're going to say, okay, that's equal to the natural log of 256. That's our initial pressure, divided by PT, which this is what we're solving for. All right, we multiply that out. This times this will give us this guy, 1.4892, and that's going to be equal to the natural log of 256 divided by PT. Let's see. All right, what we're going to do is we're going to take the inverse log of both sides. Okay, that's how you get rid of a natural log. So the opposite of a natural log is taking E and raising it to the power of that value. And so on your calculator, you're going to hit second natural log, and it'll say E raised to the power of, and then you write 1.4892. When you do that, the calculator will tell you this. Let me try that. 1.4892. I get 4.43. I get this value. Okay, so E raised to the power of that will give me another number. E raised to the power of all this. Well, E will cancel with this, and so that's how we get rid of the natural log, is we take E raised to the power of. Natural log is equal to log base E, and so if we take E raised to the power of this, then it's gone. The whole thing's gone, okay? So we have 256 divided by PT, and so 4.4335 is equal to 256 divided by PT. Cross multiplying, PT times that is equal to that. I think if we divide both sides by 4.4, we get our answer. So if we divide that by 4.4335, I think we get our answer. 256 divided by 4.4335, and we get 57. So we divide both sides by 4.4. So this is PT times this. So PT times which that looks like platinum to me, the symbol for platinum. So 4.4335, that's equal to 256. And then if I need PT by itself, I divide both sides by 4.335. So I'm just showing you all the algebra, making sure it's clear. That will be gone. PT will be equal to that divided by that, which gives us 57.7. Beautiful. Okay, and this is an example of how to use an integrated rate law. You have to use the correct equation. You do not need to memorize the equations. They are in our star sheet or our chemistry formula sheet. So let's look for that. Let's look. So if we go to Canvas, AP formula sheet, it's right there. We open it up. We go to the section that says kinetics. It's right there. Here is our three equations we got. These are our integrated rate laws. Looks like we just used this one. This is our first order integrated rate law. Or is this zero order? This might be zero order. I'll have to look in the notes. This is first order here. Oh, that's ln of 2. That's what that is. ln of 2 divided by k. So the equations are in here. These are different forms of it, though. ln of AO over AT. So that's first order. I think it's the same one as this one right here. This is first order. This is second order. Looks like it's not giving us the zero order. That's interesting. It's the only two we got. And then this is the half-life equation. Okay. Okay. So 57.7 torr is our answer. And this problem would be the exact same if everything was in concentration. Our concentration would be 57.7 moles per liter. Okay. So don't let that throw you off. All right. Half-life of the reaction is the time it takes for a reactant to drop half of its value. So we think about this when we're doing like nuclear decay. So the half-life is the time it takes for half of the substance to disappear. So let me do a little visual demonstration to show you how half-life works. And usually I do this in class, and it's kind of fun. So I take a blank sheet of paper. I got a blank sheet of paper, copy paper. I'm going to fold it in half, and then I'm going to draw on half of it. So I'm going to scribble out this whole side. Okay, and then I'm going to make a chart here. Let's say number of half-lives will be one of our column. Original. This will be the original substance, and then this is going to be what is. Let's see. I'm trying to think of the terms here. Original material, and then this will be the decomposed, the daughter product. This is what remains. So this is the original remains, the original amount, and then this is the broken down. This is the decomposed. Okay. So after 0 half-lives, when I have the paper, it's all just one sheet of paper. I have 100% original. Nothing is broken down, so 0%. Okay, and we can convert this into fractions. So this is going to be, so no fractions yet because it's 100% and 0. But I'll write it as percent and fraction. So the white paper will be unaltered. Okay, so this is unaltered. Unaltered original material. And then this will be broken down. This will be the stuff that I've crossed off. It's broken down, so it's decomposing. Okay. Okay, that's going to be the daughter products if we're talking about a nuclear reaction. So at the beginning, we have no half-lives. We have the original material. We have 100% of the original material, and the material will split. It'll break down. And so at the beginning, we have 100% original, which is this white paper. It has not been altered. And so we can write altered here. How about that? Altered. We have, so none of it has been crossed off. It is 100% white paper. Now I'm going to fold the paper in half, and then I'm going to alter one half of it. Exactly one half. All of this has been altered. So after one half-life, I have 50% that is original. Everybody see the 50% there? It's half the paper. And I have 50% of the paper. So over here, this part is also 50%. That's been altered, right? It's been drawn on. So I have one half and one half. Excuse me, I'm burpy. I just had a bunch of fried fish, so excuse me. So we've got, that's after one. Now I've got to take this, I already folded it in half. So now I'm going to take this again. I'm going to fold it in quarters. And what is that going to look like? So half of this is already altered. Okay. And so imagine that this side is flipped back. So this is all, I'm going to fold this in half again. And so I'm going to have this showing, and what's remaining is going to be covered. Okay. So imagine me taking this paper. It's already in half. So I've got half, right? And then the other half of the paper is on the back. It's folded. And so now I'm going to flip this in half. I'm going to fold it inwards, right? And I'm going to get fourths, and I'm going to cover one of those fourths. And so now I have 3/4 altered, 1/4 remaining. So this is after two half-lives. I now have 25% or 1/4 remaining, and 75% of it has been altered. 3/4 has been altered. That's after that's after two half-lives. Okay. Now picture I'm going to do it again. Let me clean this up a little bit. This is messy. I'm so glad this mouse works with me. Okay. Let's circle the fractions here. Okay, now I have a fourth, and so I'm going to take a fourth, and I'm going to cut it in half. Okay, so I'm going to take this little box, and I'm going to fold it in half, and I'm going to cover and alter half of it. So this is 3 half-lives, and so we're going to have half of 25%, which is 12.5%, which will be 1/8. This will be 100 minus 12.5 is what's going to be broken down. 87.5%, which will be, what is that in a fraction? 7/8. All right, let me try that. 7/8. Yep. So that'll be 7/8 as a fraction. So 7/8 will be broken down. 1/8 will be remaining. Okay, and then in fourth, it'll be 1/16. This will be 15/16. And then we'll do it one more time. 5 half-lives will be 1 out of 32. And then 31 out of 32 will be broken down. And it can keep going. 1 out of 64. 63 out of 64. Okay? All right, and so this is showing us how half-life works. The half-life for a reaction is the time it takes for half of the reaction, or for the reactant's concentration to drop to half of its original value. So how much time does it take to cut the concentration in half? Right, the concentration of the reactants is being used up. The half-life, or T1/2, is the time it takes for half of its original value to drop, okay? Or half of the concentration to drop to half of its value. So if I started a reaction and my concentration of my reactant A was 1.0 molar, the half-life will be when A 1/2 will be equal to 0.5 when the concentration's half. And then after another half, will be 0.25, and then 0.125, and so on. Each half-life it'll split in half. And I hope this helps. If this doesn't make sense with the folding, then actually take a piece of paper and fold it. Take a piece of paper, fold it in half, and then cross out half of it. Cross off, exactly. So now you got a paper that is folded and it's got half of it colored. Now take that, fold it upon itself. Now take it and fold it again so that it folds into fourths. Open it back up and cover half of the remaining white side. So when you start this, so let me go through this again because I think this would be good for you guys to do. So I take a piece of paper, I'm going to fold it in half, okay? And then I'm going to color or alter half of it, okay? And then I'm going to close it back up. I'm going to fold it into fourths. So now I got 1/4, and this side's already covered, right? I've already covered that side. And so now I'm going to look at what's left. This is what's remaining, and half of it is going to decompose or be used up. And so now that's what I'm going to have. And then this is what it's going to look like after an eighth. So we're going to cut this into halves. And then this side will be all used up. All of this stuff. I'm trying to make this kind of neat. So all of this will be used up. I wish I had some kind of some other tools here, but all this will be used up. And then we're going to cover this one as well. And so all that is remaining is 1/8. Y'all see that? So this is 100%. This is 1/2. This is 1/4. Now we have 1/8 remaining. Then you can take it and fold it again. Let's see how that would look like. So this is my 1/8. Then I could cut it again, 1/16. All right, and then everything will be covered. Everything except for 1/16, which will look like that. Okay, and it's hard to tell, but I hope you guys don't understand what I'm saying. I actually fold the paper and you'll see, and it's pretty cool. And you can see how half-lives work, and you can make that table. Okay, so I hope that helps with what a half-life is. It's the time it takes for half of the concentration, the initial concentration of the reactants, to decrease or be consumed so that it's got half of its original value. All right, for first order reactions, this is the half-life equation. It's KT, so K times the half-life is equal to the natural log of 2, and the natural log of 2 is 0.693, so it might be easier to just remember 0.693. Okay. All right, for first order reactions, the half-life is independent of the initial concentration. Okay, and that means that the concentration of the reactants will be cut in half every half-life. So it's a first order reaction. It's linear. Okay. Half-life is independent of the initial concentration, and the concentration of the reactants will be cut in half every single half-life. Okay, and we'll have to do some practice with this. Ernest Rutherford is given credit for discovering the concept of radioactive half-life. It was later shown that the same math applies to the kinetics of first-order chemical reactions. Very cool. Second-order reactions. Here is our rate law. And it's not the rate for A times B. It's a squared rate on one reactant, right? That means that if the concentration is doubled, then the rate is squared. So the rate will be quadrupled. Or if the concentration of the reactants were to triple, then the rate would be multiplied by 9 times. Okay, so that's a second order reaction. Here's the integrated rate law for a second order reaction. Let's see what this is. This is our rate constant, K, whatever its value is. They would give us this value in these equations. It's 1 over the concentration at time t. So if you wanted to know the concentration of the reactants at 3 minutes, then this will be the concentration at 3 minutes. This is what we are solving for. This is our unknown. over, so it's 1 over what we are looking for, the concentration at time t, minus 1 over, or the reciprocal of, the concentration of the reactant initial concentration. So this is our second rate law, integrated rate law, and this is the half-life equation. The rate constant times the half-life is equal to 1 over the concentration initially. All right. In this case, the half-life does depend on the initial concentration of the reactant, and the half-life changes with time. Oh, man. So we usually will not calculate the half-life for a second-order reaction. That's usually not an example. Usually when you're dealing with half-life, if you see any kind of questions with half-life, just assume it's a first-order reaction. So let's go back to that. So first-order reaction. Come on now. First-order reaction, we're going to be using half-life, or half-life is first-order reaction, and it'll be this. K times T is equal to 0.693, or better yet, T1/2 is equal to 0.693, or the natural log of 2, divided by K. That's baby K. So that is our equation, and I think that's what you'll see on your formula sheet. The half-life is equal to 0.693 divided by the rate constant. That'll tell you the time it takes for half of your reactants to disappear. Okay, and then here's our integrated rate law for the second and half-life equation for second-order reactions, which I've never, ever seen a problem like this. Okay. All right, now, if we plot a straight line, if we plot a graph where 1 over the concentration of A at time t, so 1 over the concentration of our reactant. If we plot a graph like this now, we get a straight line slope with slope equal to K. All right, and so the slope of that, the rise over the run, okay, the slope equals K. It's a positive slope. This is 1 over the concentration versus time. So time's always on the y-axis, but for a second-order reaction, we don't see a straight line until we do 1 over the concentration. So the reciprocal of the concentration. Reciprocal of the concentration is a straight line. And we can only really work with straight lines in AP chemistry because curved lines require calculus because the rate is changing every second. But we need a linear relationship, okay? And so the reciprocal of the concentration will give us a straight line with the slope equal to K. All right. Okay, above equations do not apply to second-order reactions that are first-order and 2 reactants. So if it's got to be second-order for that reactant. So what does that mean? The rate law needs to look like this. It needs to have 1 reactant that has a second order for that reactant, and then this will be the integrated rate law for that. It does not apply to equations that are overall second order. So what does that mean? So if I said that my rate for my reaction was equal to A to the 1 times B to the 1, well, that's not a second order. It is an overall second order, yes, but these equations are when it's like this for 1 reactant. Okay, so 1 reactant needs to have that Ka raised to the power of 2, and then you can use a second order integrated rate law. Not when this is the case, so we can't use that. Okay. Okay, first order reactions, K times T raised to the 1/2 is equal to 0.693, or ln of 2. And then here's the integrated form. So this is a half-life equation. This is an integrated form. Here is the slope, or the graph, for the natural log of A. So when we take the natural log of A, we get a graph that has a straight line. Okay, and the trick to this is you need to be able to look at graphs and determine whether it's a first, second, or third order. Okay, or if you're given equations, you should be able to determine first, second, or third order. So if it's a first order reaction, the natural log of the concentration will give us a negatively sloped line where the slope is equal to the K value, but then we flip the sign because it's a negative slope and K cannot be negative. Okay, so whatever the slope is, just flip the sign and you get the value of K. Right, the slope is equal to K. Now, if we have a second order reaction, this is our integrated rate law. This is our half-life equation. And the graph will be linear only when we plot the reciprocal of A. Here's a couple of ways to remember this. It's natural to want to finish first. It's natural to want to finish first. So first order reaction is natural log. I like that. I've never seen this. That's awesome. It's natural to want to finish first. First order reactions are natural logs. That's great. To want to finish second, that's upside down thinking. If you want to finish second, that's upside down thinking because you're going to want first, right? So that's reciprocal. So that's a good way to remember these two. Okay. Now, we didn't say anything about zero order reactants, so let me get my notes and look at that because we're going to need to look at that. Let's see. Okay, so let me just make a graphic. So ignore this, what it says here. Okay. Zero order. So zero order. Let's look at some stuff. Concentration versus time will give us a graph. The K slope is equal to negative K. All right, so if you plot the concentration over time, you get the slope of negative K. And here's our equation. The concentration of our reactant, let's say it's A, that's our reactant, is equal to negative K times T plus the initial concentration of A. Does that not look like an equation you guys have seen before? Does that not look like Y equals mx plus B? Yes, it does. It's the same form. So that's our zero order rate law, integrated rate law. Now let's look at first order. First order. Remember, it's natural to want to finish first. So that means that the natural log of our concentration of A over time will give us a negatively sloped line. And the slope is equal to negative K. So let's write that. Slope equals K, negative K. All right, for our natural log, for our first order, the natural log of A will be equal to minus K times T plus the natural log of our original concentration. So that's the first integrated rate law. And the slope will be equal to minus K again because it's negative. Now when we do the second order, the third graph, second order reaction, we have to take the reciprocal of the concentration. These are all AT. So when we take 1 over the concentration of A, or the reciprocal of A, or the reciprocal of the concentration over time, then we get a straight line, and it's positive. So this slope equals K. And here's our equation, 1 over the concentration of A. This is at times T. Oops. This is what we're solving for. 1 over the concentration at time T is equal to KT plus 1 over the concentration of the original concentration. Okay, so the slope is equal to K. And another way that I remember this is 0, 1, 2. Zero order reaction, first order reaction, second order reaction. Which things will make a straight line graph for a zero order reaction? It will be the concentration. So C. And then for a first order reaction, the only way you're going to get a straight line is if you do the natural log. So CL and then R. So CLR is what I use to remember first order reaction of concentration versus time, right? Concentration versus time, that'll give me my straight graph. Second one is, CLR. CLR. CLR, yeah, CLR. So the L is the second order. You need the natural log versus time to get that straight line. And then R is the second. Messing up here, sorry. So 0, 1, 2. 0, first order, second order. All right, and this is most of the integrated rate law stuff. We will practice doing some of this. It does have some nasty algebra, but we should be okay with that. And there's not a whole lot of questions with that. Most of it's these graphs. So that's most of the integrated rate law stuff. If you guys want to follow what they did in the NIMSY notes and do the graphing technique, you can, but I don't do that. I don't find it very useful. I'm sure it has its usefulness, but I just don't do that. Okay. What does this say? Why does the temperature affect the rate A times B? And that's because as the temperature goes up, the rate constant goes up. Collision model. The collision model explains how the rate is affected by the concentration and by temperature. Okay, you have a higher concentration when you have higher temperatures. And we'll talk about the collisions. All right, so when you have more concentration, you have more collisions per second. So if you have more stuff in there, more concentration, more ions in solution, you're going to have more collisions per second at that higher temperature. And that's what makes the rate of the reaction happen. You will have more collisions that are successful in producing a product. Okay, and we got to talk about the collision model. All right, faster particles at higher temperatures will have more collisions per second, and then we will activate the energy. We will have enough energy to overcome that activation barrier. So the activation energy will be able to overcome that activation energy if we have sufficient temperature. Because the higher the temperature you have, the more energy you got, and then those molecules will be able to hit each other with sufficient energy to overcome that barrier, and they will become products, or they will be kind of on their way to becoming products. Okay, so here's our graph. This is our reactants. This is energy versus time. The reactants must have some kind of energy that they must overcome in order to become an activated complex or a transition state. Which is something that is halfway between a reactant and a product. Okay, so you've got to form that transition complex or that transition state or that activated complex, which is right up here, and then you can start to produce products. So if this is the activation energy for the forward reaction, so let's say A plus B is making C, this is the activation energy for that reaction, where this is A and B, and then this is C as a product. Now, it is important to note that this is the activation energy of the reverse reaction, where this guy is going to go backwards. It can work the same way, where this is just a bigger hump. And that's why reactions that are generally one way, like this, it's going to need some kind of push, but then it's going to get moving. It'll get over this hump, and then it'll make products. It'll come down, rolling down the hill. So if that's the forward reaction, the reverse reaction is really not possible and not likely, because this is a huge energy barrier, and it's got to overcome that, right? Just like a ball wouldn't roll backwards and uphill on its own, right? You're going to have to push it really hard to get it up this hill. And so the forward reaction is more likely, more feasible. And so most reactions, or some reactions, I can't say most, but some reactions that are one way are said to go to completion, meaning that there's no return trip. But the truth is, most reactions are reversible, and as soon as you make those products, they're going to be falling apart and going back and making the reactants. And so reactions can go both ways. And equilibrium is a state. I'm not spelling this right. My brain is not working. Equilibrium is a state in which the forward rate of the reaction is equal to the reverse rate. So that's what we call equilibrium. And that means that there's no change in the concentration over time. So you can have a reaction where you've got A plus B makes C plus D, but as soon as they get together, the reverse is equally as possible. And that means that the forward push is equal to the reverse push. And it's like a tug of war where nobody wins. And so the concentration of all of our reactants and all of our products will not change over time. So it's like a stalemate. And so that's how equilibrium and kinetics kind of connect, is that the forward rate is equal to the reverse rate when we're at a state called equilibrium. And then you guys already know how kinetics is related to energy, because, you know, in thermodynamics, because we've been talking about these graphs already. And we talk about heat them up and molecules moving, and so it definitely relates with thermodynamics. Activated complex, the temperature arrangement of atoms between. Okay. So the activated complex, the transition state, the intermediate complex, intermediate state, these are all same thing. This is something that's an arrangement halfway between the reactants and the products. Okay. All right, change in energy. It is positive for endothermic. It is negative for exothermic reactions. We already know this. Okay. It has no effect on the reaction rate. Okay. So the change in energy, this hill, what? Oh, the change in energy, positive or negative. Okay, whether it's positive or negative has no effect on the rate. So whether you're endothermic or exothermic doesn't matter. The rate will still depend on the temperature and the concentration of the reactants, surface area, and all those things. Okay, so for the reaction to occur, so here's a reaction. Chlorine plus nitrosyl chloride will react to form chlorine and nitrogen monoxide. All right, in order for this reaction to occur, the molecules must interact with each other in a particular orientation. Okay, so only when they collide in a certain way will the reaction proceed. Okay, so reactants have to hit each other with correct orientation, not just any random orientation. They must hit up kind of like a lock and key fit. If you're going to make a product, you're going to need a lock and key fit. They're going to need to fit together in order to make that product. And if they don't fit together properly, then you're not going to have a reaction. They must also hit each other with sufficient energy. The temperature must be high enough so that the energy of the collision is great enough to overcome the energy barrier. Because if they're not going to hit each other enough with the energy, they'll just bounce off, nothing happens. But if they hit enough with enough energy, sufficient energy to overcome the activation barrier, then they will climb that activation barrier, they will make the transition state, and you will get you will form the products. Okay? So for a given reaction, the activation energy relates rate constants at two different temperatures. Okay, and we'll be talking about activation energy another time. All right, so the activation energy relates rate constants at two different temperatures. So the natural log of K1 over K2, so these are two different constants at two different temperatures, and that's equal to EA over R, 1 over the second temperature minus 1 over the first temperature. Okay, and we don't use this equation much, but we'll talk about activation energy a little bit. Oh, this is R. This is a gas constant. This is a constant that you have in your formula sheet. Let's see, where is that? Where is R? R is up right, maybe in thermo. Right here. There we go. That's the gas constant R. Now see that 8.314. There's also so this is the energy R that we use for that equation. There's also a gas constant R that we use for gases. So those are two constants that we'll use. See if there's any other constants we use here. Here's Avogadro's number. We'll use that one. Okay. Okay, and here's an example using an equation. I'm not going to go through that right now. Okay. Okay. Reaction mechanisms. Okay, this is the process by which reactions occur. So what actually happens from going from the reactants to the products? All right, sometimes the mechanisms are dependent on temperature. So there are each step, and so they're called elementary steps. So any one baby step in a reaction is called an elementary step. Okay. And then a reaction's molecularity is defined by the number of particles that participate as reactants in an elementary step. All right, and we'll see some examples of this. There's three terms. There's unimolecular molecularity, so they can be unimolecular, they can be bimolecular, or they can be termolecular. And what does that mean? That means that, so if it's unimolecular, it's usually a decomposition reaction where you have only one reactant and it is breaking down into something else. So only one reactant, only one molecule, only one mole in the balanced equation. Now bimolecular means two, and that means you have two things, or you could have two things. So it could be 2 moles of this. That means that you have 2 moles of this that react together to have the reaction happen, or you can have 2 different substances. But either way, you have 2 molecules. It can be 2, let's say this is nitrogen monoxide gas. You can have 2 moles of that, or you can have 2 different things added together, so 2 reactants. Or you could have termolecular. So maybe you could have NO, so 2 of those plus O3 will make something. So you've got 2 molecules there, and then a third one. So this is termolecular, which means more than 2. And those are kind of rare. So usually they're unimolecular, or usually they're bimolecular. Bimolecular is most common. Okay. For multi-step mechanisms, sequences of elementary steps are needed to go from the reactants to the products. Okay, so here's our reaction. Nitrogen dioxide plus CO will make nitrogen monoxide and CO2. So let's look at the elementary steps for exactly how this reaction happens. Which molecules need to collide with which ones in order for this to work? Okay, so there's 2 elementary steps. We can take 2 of these guys. They can react together to form this and this. And then step number 2, we can have NO3 to form this, or NO3 plus this to make these. So each of these is a step. And what they do is they will cancel out. So these 2 steps, these 2 elementary steps, must add up to give up the overall reaction. And so most of this, guys, will be looking at a chart like this, kind of like we did with Hess's law. That's another reason why I did thermo before this chapter. So it's kind of like Hess's law. You need to be able to prove that these 2 mechanisms add up to make the overall reaction. Just like when we did Hess's law, you add up all the reactions to give you the target reaction that you were looking for, right? It's the same thing. So here, NO2 is a reactant in this step, but it's a product in this step. So it's produced here and then consumed, and so it kind of consumes itself, and it's canceled out. Same thing here. So NO2 and NO3, these are both called intermediates. An intermediate is something that is consumed in one step, produced in another. Notice that one of these, okay, well, it's hard to say with NO2 because NO2, there's still another mole here that survives. But notice that NO3 is produced in this step and then consumed in this step. And notice it's gone. It's not in our balanced equation. That's what an intermediate is. Okay, it's produced in one step but then consumed in another, and so it is part of the reaction, but it's not in the equation. Okay, and that's different than a catalyst. A catalyst is present in the reaction, but it can reappear. Okay, it's not written in the equation, and it's not canceled out either. Okay, so what's left? We have NO2 right here. We have CO right here. NO right here, and then CO2. So do these 2 add up to give us a total reaction? Yes. And so we would say yes, these mechanisms are possible. This is a valid mechanism for this reaction because it adds up to our reaction. So we need to check the stoichiometry and make sure that when things cancel out, we actually get the overall reaction. So we must check the stoic. We must check that stoichiometry. Okay. And then the next part of mechanisms, it must correlate with the rate law. Okay, and we'll talk about that. So that's our two requirements for mechanisms. They must agree with our stoichiometry, and they must agree with the rate law. Remember, the rate law is experimentally determined. So they must agree with the stoichiometry of the balance equation, and they must agree with the experimentally determined rate law. All right, NO3 is an intermediate, and all multi-step mechanisms have them. There's usually intermediates. Okay, the rate law and relative speed of each elementary step, no matter how many there are, determine the overall rate law for the reaction. That is, the mechanism gives us the overall rate law. Rate laws for elementary steps are found as follows. All right, so here is our molecularity. Uni by, so this is A, so there's only one thing breaking down, so that's unimolecular. This is bimolecular because you have two molecules. So that might even look like this, 2A. So 2A to P. That would still be bimolecular, okay? So we write them separately, but if you put them together, it's still 2 moles, so that's still bimolecular. So A plus B is also bimolecular, and then these have more than 2, so these are termolecular, which are kind of rare. All right, so the rate law for the elementary step for a unimolecular reaction is K times the concentration of that reactant. Only one reactant. Okay, if you have 2 of them and it's bimolecular, then it'll be A squared because you got 2 of them. All right, if it's bimolecular but it's A plus B, then it'll be A times B. Multiply their concentrations. If it's termolecular, A times A times A, it'll be A to the third, A times B, A squared times B, and then A times B times C for that one. Okay, so this is the molecularity. Unimolecular means that there's one thing involved in the reactants. Bimolecular means it's 2, even if it's 2 of the same thing. Bimolecular is 2, and so that's the rate law squared, and so on. The rate laws are for elementary steps, not necessarily for the reactant products. So these are for elementary steps. Let's go back. What is an elementary step? Let's go back to this slide. So here's our reaction. This was our overall reaction. But we can write rate laws for these guys, each of these elementary steps. Right? This whole thing is a mechanism, and these are each individual elementary steps. So we can write rate laws for them. So they apply to each elementary step, not necessarily the overall rate law. It may not reflect the overall rate law, but we could write a rate law for each of these elementary steps, and that's easy to do. Harder to write it for a whole reaction. Okay. All right, most reactions have multiple elementary steps. The slowest step is called the rate determining step. Okay, think about when you're driving on the highway, you get behind somebody that's going slow. Their speed is limiting how fast you can go, right? Or if you're on a football team, you know how they say like the weakest player, the team is only as strong as their weakest player, right? Because if anybody goes through that player, then they get through the team. So the rate determining step is the slowest, and that's the important one. Okay, that's the step that the whole thing depends on, right? So if you're going down the highway, you can only go as fast as the person in front of you. Person behind you can go only as fast as you. And so if you've got somebody slow in the front of a carpool, their speed is going to limit everybody else. And so you're only going to get there as fast as they will allow you to because you're stuck behind them, right? And we all hate that. All right, so for a rate law to be correct or to be valid, the rate law must be valid on the rate determining step. I had to give me a second. Rate determining step. So the rate law is going to be based on the rate determining step. The rate law will be based on the slowest step. It will not depend on the faster steps, right? The reaction rate is only as fast as its slowest step, right? Just like if you were to race with teams, You had 6 people. If you had a slow guy on your team, and you say, okay, when you race, all teams of 6, each team basically, let's see, you're only as fast as your weakest link, right? And so you're going to be limited by that slowest step. Okay. Okay. And then you're only going to have reactants in it, only not intermediates. So you can't have a rate law with intermediates in it. It can only have reactants in it. Intermediates will not be in the rate laws. Okay. These are supposed to be arrows here. So if we've got this equation here, these are the elementary steps. State the rate law and the units of the rate constant. So let's go through this. So the rate, so what's our slow step? What we're going to do here is find our slow step and draw a line underneath it. We will stop there. We're not even going to look at this next one. And these are supposed to be arrows. Okay, so this is our slow step. Notice that this is our reactant, and it will go in our rate law. There's only one molecule of it, so there's only one molecule here. So it's raised to the power of 1. And then chlorine will go here, raised to the power of 1 because it's just 1. All right, notice that the other elementary steps are not in our rate law. They're only dependent on the slow step. All right, so rate will be equal to the K. And when we say K2, we just mean the K value for that reaction, that second elementary step, our rate determining step, our slowest step. So that's what K2 means. It just means it's the K value for that reaction, not necessarily the K value for this whole thing. Okay. So chlorine is not a reactant here, though. So we cannot write the rate law on that. Why is chlorine not a reactant? Because it's not here. Look at our overall reaction at the top. Here's our overall reaction. Cl by itself is not in there. Okay. Chlorine is created in that first fast step. It's also at equilibrium. That's what that means. And then it's consumed here. It's not in our overall reaction, so it's not a reactant. So we must restate this rate law in terms of our reactants. So for fast steps, you can write a rate law in either direction. So we can say K1 forward, which is Cl2. Right, so if we were looking at this reaction forward, if it's at equilibrium, we can say, okay, the rate that way is forward. So chlorine to that rate equals KCl2, the concentration of that disappearing. Or we can write the rate of the reverse, which will be this way, reverse. And so that'll depend on the chlorine. And it'll be squared because there's 2 molecules of it, right? All right. So we can write the forward and the reverse. So chlorine is equal to K1F divided by K1R reverse. And that's the times the chlorine raised to the 1/2 power. So we can look at this reaction. So what are we doing here? We are saying that the K for the first step forward is equal to, oh no, we're saying rate of 1 forward is equal to K of 1 forward times Cl2. Okay. And then we're saying the rate of 1 reverse is equal to the K constant for 1 reverse times Cl squared. Okay. And so what we can do is solve this for chlorine. Okay. So we're saying rate of that K divided by K. I'm not sure what this is supposed to be. Maybe an arrow? Not sure what these boxes are supposed to be. But we can rearrange this and see what chlorine is supposed to be equal to, and then we will substitute it in. All right, and I'll find another example where we do this and make sure it's clear. So we'll need to look at that. So we will substitute this in for chlorine above, K1 forward divided by K1 reverse times the concentration of chlorine raised to the 1/2 power will be equal to chlorine, and then we plug that in for this. So then we write our new rate law. So there's our new rate law. We had K originally, K2. We had CHCl3, it's still in there. But we can't write chlorine, but we can write Cl2 raised to the 1/2 power. Okay. And then we got our units there. All right, a catalyst is going to speed up the reaction by changing the mechanism that it undergoes and speeding up the process. It's going to change the way that we make the activation state. Okay, it's not consumed during the course of reaction. And then when reactions are catalyzed or uncatalyzed, it's going to have a completely different mechanism. All right. This is why catalyzed and uncatalyzed reactions have different activation energies, because it's going to change the reaction pathway. And then there's something called homogeneous catalyst, which is present in the same phase as the reacting molecules. So if it's an aqueous reactant, then the catalyst will be aqueous. And then we have heterogeneous catalyst, which means it's a different phase. So maybe it's a gas or a solid, and our reactants will be aqueous or something. All right, usually a solid catalyst. Okay. And then this explains how catalytic converters work. Okay, and I'm not really worried about this. An enzyme is a biological catalyst, which will change the reaction pathway and speed up the reaction by lowering the activation energy. And it's a lock and key fit. It explains how catalysts work and how enzymes work. Okay, I'm not worried about this. Okay, guys, I think that's it. I think I've talked long enough. I hope this was helpful. Sorry about my mumbling. I hope that you guys were able to learn from this. Please let me know if you have any questions, and I will try my best to answer them. If I don't know the answer, I will look it up. Okay, I'll try to figure it out for you. All right, guys, have a great one. Thank you.